So, okay, proof of some facts. Yeah, Joe. Proofs of the of some facts that are left as an exercise. One. Suppose A, B are integral domain. Then AX is also an integral domain. Proof. Okay. Let f equal to a0 dot an xn belongs to ax, g equal to b0 bmxm belongs to ax, and an not equal to 0, bm not equal to 0, ai belongs to a, 0 lesser equal to I, bj 0 lesser equal to m. If g equal to 0, then কি হবে a0 dot 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 anxn b0 bmxm equal to 0, a0 b0 an bm xm plus n equal to 0. Okay, so see, now comparing the coefficient, from the both side of the equation, we get an bm equal to 0, but we assume that n not equal to 0, bm not equal to 0. So if one of them, that is either f or g, is not 0, we have a contradiction. Just put the first part. Okay. The proof is fine, right? integral domain. Then A cross is same as AX cross. What is A cross? A cross means set of all units. Let A belongs to A cross. This implies AB equal to 1 for some B belongs to A. This implies AB belongs to 1 in AX also. Implies A belongs to AX cross. Conversely, suppose F belongs to AX cross. Okay, let F equal to A0 dot 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 AN xn AN not equal to 0, AI belongs to A, 0 less or equal to or less or equal to N. Since F belongs to AX cross, there is some G belongs to AX such that GX such that FG equal to 1. We take, okay, so this is unique, so don't need to take unique least degree. So let G is B0 BM BM not equal to 0, BI belongs to A, 0 less or equals to or less or equal to M. The equation Fg equal to 1 implies A0 B0 plus plus dot 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 AM AN BM XM plus N equal to 1. Since okay, no, comparing the coefficient, comparing coefficient from the both sides of the equation, let's call it something. Equation start, we see that A0 B0 is 1 and AI Bj equal to 0 for all 1 I no, that's a problematic stuff, need not be 0 and AN BM equal to 0. Since AX is also domain, and we have assumed AN not equal to 0, BM not equal to 0. So Okay, we can compare degree from the both side also. No problem. So if degree f greater than 1, then we arrive at the contradiction. But therefore okay, so please go through the proof, and if you have some problem, please ask. Is it okay, or do you want to say something? Okay. Okay, so these two things are done. So next I need to prove this problem 3. Problem 3. Okay. Problem 2, proof. Okay, proof. So where is McCoy's theorem? Just a minute. Okay, so in the McCoy's theorem, we have proved something more general about the annihilator of an ideal, which states the following: let A be an ideal in a several variable polynomial ring, and if there exists some non-zero polynomial in annihilator of A, then there is a scalar in that annihilator. So we induct on n and prove the result. But for n equal to 1 case, it is just same thing as proving the problem 2 of 3. So we will repeat the argument n equal to 1 case and we will be done. Okay, so suppose we are going this side. If is a zero divisor, that is there is some g belongs to Ax such that fg equal to 0, we may take g to be least degree polynomial. we are taking g to be the least degree polynomial for some contradiction. We want to arrive some contradiction, so we are taking g to be the least degree polynomial. Okay. Okay. Let okay. Let's write a equal to a0 plus a n xn, a n not equal to 0, a I belongs to a 0 I n, g to e bm xm, bm not equal to 0, bi belongs to a 0 I m. If okay, if degree g equal to 1, then we are done. If not, suppose degree g greater equal to 1, suppose degree g is greater equal to strictly greater than 1. Okay, so if c okay, if c into f equal to 0 for some c belongs to a star, then we are done. Otherwise, so we assume cf not equal to 0 for all c belongs to a star. In particular, what is in particular? In particular, bm f not equal to 0. Not equal to 0. That imply where is bm ai is not equal to 0 for some 0 I n, and where is okay, we choose j, no, j belongs to 1 to n just a minute. bma is not equal to 0. bma is not equal to 0 means ai into g is not equal to 0. Okay, bma is not equal to 0 implies ai into g is not equal to 0. So we choose j belongs to ai belongs to 1 to n. Maximal such that ajg equal to ajg not equal to 0. But if g equal to 0, but if g equal to 0 implies if I am offline. Okay, recording is on. Okay, so I am repeating the proof again. Suppose f is a zero divisor, that is there is some g which is of course non-zero belongs to x such that the product is zero. Now we may take g to be the least degree polynomial. There are lot of many g's. We are taking g to be the least degree polynomial such that this happens. Okay. Uh, okay. So suppose f is of the form a0 plus dot 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 a n x n, and where a n is not equal to 0, ai's are in a, and g to be of this form, this. Now if degree g is equal to 1, then we are done. So we assume that degree g is not equal to 1, degree g is greater than 1. Now if degree g greater than 1, we have to show that there is some c belongs to a minus 0 such that c is equal to 0. If there is some c which satisfies this condition, then we are done also. So we assume that this condition is not satisfied by any c belongs to a minus 0. That is cf not equal to 0 for all scale non-zero scalar, cf is not equal to 0. So in particular we take c to be the bm. So bmf not equal to 0. Now bmf not equal to 0 implies bm ai is not equal to 0 for some ai. Why it is f? This is f. So bm is multiplied by bm. So it is non-zero means at some coefficient this is non-zero. bm ai is non-zero for some 0 lesser equal to or lesser equal to n. So bm ai is non-zero means ai into g is non-zero, because we at least get, if I multiply ai with g, we know that bm ai is not equal to 0, so we can say that ai into g is not equal to 0. Now we are choosing j belongs to 1 to n, the maximal, such that this holds. There may be there at least one ai for which the condition satisfies. There may be a lot of ai. We are taking the maximal ai, maximal j, such that this condition holds. Suppose a1, a2, dot 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 a11, a12, a13, a20. Suppose it holds for 3, 4, 5, 10, and is a 0 for everything else. So we are taking for example 10. So such that this condition is satisfied, that aj g is not equal to 0. Now if g equal to 0, that implies a0 b0 plus dot 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 plus what is an bm xm plus n, that is equal to 0. Okay, so if we compare the coefficient from the both sides, okay, so this implies bm aj is also 0. That is bm aj is also 0. This implies aj g is also 0. That is a contradiction. Yes, the proof correct. Okay, f g equal to 0, this is 0. So comparing the coefficient from the both side, aj into bm, this is m plus j term is also 0. So aj into g is 0. Okay, fine. So aj into g is 0. So this implies that contradiction of the fact that cf not equal to 0. This implies there is some c belongs to a star s such that cf equal to 0, and we are done. For the converse part, it is obvious. If CF equal to 0, then yes, of course, F is a zero divisor. So this part is done. The further generalization part, we will stick to the proof of McCoy's theorem. Where it is, okay. So I have not proved 3 and said it is follows from the McCoy's theorem, but okay, I proved it now. And for the general case, we will stick to the McCoy's theorem. One, two, this, and I have to repeat some more proofs. Okay. Repeat some more proofs. If F is nilpotent, then the coefficients are nilpotent. Proof. This side. Suppose F is nilpotent, that implies nilpotent. Let P belong to spec A and consider the ring morphism AX theta A mod PX. Take any polynomial A0 dot 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 AN XN that is mapped to A0 plus P plus dot 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 plus AN plus P XN. Okay. Observe that kernel theta equal to Px and Ax mod Px is isomorphic to A mod Px. Now F is nilpotent, that implies theta F is also nilpotent. Since A mod P is domain, this implies A mod Px is also domain. This implies theta F is nilpotent, means theta F is 0 in A mod Px. That is A0 plus P plus dot 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 AN plus P XN equal to 0 plus P. This implies AI plus P equal to 0 plus P for all 0 lesser equal to lesser equal to n. This implies AI belongs to P for all I is for all 1 less 0 lesser equal to n. This implies AI belongs to intersection P belong to spec A for all 0 lesser equal to n, as P belongs to spec A was arbitrary. Therefore AI belongs to root 0 for all 0 lesser equal to n. AI is a nilpotent. Converse part. Suppose this part is follows from the fact this. Okay. If A0 dot 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 AN belongs to root 0, this implies A0 A1x ANX xm belongs to okay, so now I have to mention what do we mean by root 0. So replaced by nil a. Nil ax. So since a0 is in nil a0, so a1x is in nil ax. A1 belongs to nil a, implies a1 n1 equal to 0. This implies now a1x whole power n1 equal to a1 a1 n1 x n1. This implies 0. So a1x belongs to nil ax. So like that, all r belongs to nil radicals. This implies a0 plus 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 an xn belongs to nil ax, as nil ax is an ideal, that implies a belongs to nil ax, and we are done. Okay, so now we need to generalize these results. Okay, we have already done the part. Okay, where is the part here? Okay, so we already proved the first one, that if a several variable polynomial is a unit, then that a this part, the constant part, is unit and rest of them are nilpotent. So we generalize the statement for part 2 as follows. We just copy it and paste it. This gives our generalization statement. Generalize the results. Suppose is nilpotent. Then all coefficients of f are nilpotent. This is our claim. So proof. We induct on R the case R equal to 1 has been proved in exercise 2. For R equal to 2, let f equal to a0 an, okay, an yn belongs to ax y. Axy is same as ax y, same as ayx. Okay, where an not equal to 0 and ai belongs to ax 0 I n. Since f is nilpotent, this implies a0 an belongs to ax are nilpotent by exercise 2. Again, using the same exercise, we let aj is equal to a j comma 0 plus dot 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 plus a j comma mj x power mj. J varies from 0 j n. aj mj not equal to 0 for all 0 n and a ij belongs to a for all ij. So again, using the same exercise, we can say that aij is nilpotent for all ij. This proves the first part, and the converse part follows from the same argument. Use because nil a xn is an ideal. Use. So this okay. So I guess I have proved all the stuffs that I left. Yes, let me check. Yes, everything is completed till the last class. Okay, problem 4. Now today's business. Okay, anyone done problem number 4? Hello? Hello? No. No. Anyone has done that problem number 4? In the ring Ax, the Jacobson radical is same as nil radical. Anyone else? Anyone else?
ना भाई वो क्या जिज्ञेस को
I know she is excited, but okay. Oyon? Oyon?
तो करो मैंने
Okay, let's solve it in the class. First of all, tell me that okay, root 0 and Jacobson radicals are two ideals. So, can you say which containment is trivial? I mean, for any ring, which containment hold? Nil radical is in Jacobson radical or Jacobson radical is in nil radical?
मैंने मैक्सिमल आइडियल একটা প্রাইম আইডিয়াল হবে মিল থেকে জ্যাকবসনটা যাও মানে ম্যাক্সিমাল আইডিয়াল একটা প্রাইম আইডিয়াল হবে nil radical is contained in Jacobson radical.
Yes, that's true. That's the trivial part. It holds for any ring. We have to prove the converse part. Okay. So everyone okay for recall. I am recalling a definition. Recall Jack A. The Jacobson radical of A is denoted recall. Which color should I use? Is it good? Ah, fine. That's a nice. So for any ring A, we define recall. We define Jacobson radical of A to be as follows. Jack A intersection M belongs to max spec A. Intersection of all maximal ideals is called Jacobson radical. Okay, is the color is healthy for your eyes, or should I change to any other color? What about this? This also fine. We can use this. You can use this.
Yeah, ठीक है.
Or this. Which color is this? Light gray. We can use light. We can use light gray. Light gray is fine, I guess. This to a different color. I guess. Let's change it to the light gray. Okay. So for any ring A, we define Jacobson radical as intersection of all maximal ideals. So okay, note that for any ring A, we have nil A is contained in Jack A. Some author call it radical ideal also. Jacobson radical as radical ideal. Okay, what is the proof? Okay, what is the proof? Please, anyone, what is the proof that nil is contained in Jacobson radical?
So max spec of any ring is contained in spectrum of the ring. Then
Yes.
taking the intersection, then intersection of all P belongs to P belongs to spectrum of A or A is contained in intersection of M belongs to max spec of A.
You are saying that larger collection gives smaller intersection.
Yeah,
But then you had to prove it set theoretically.
yeah.
Okay, that's fine, that's all works, but okay, we need to prove it more rigorously. Let X belongs to nil radical, that is intersection of all prime ideals. P belongs to spec A. Oh, we don't need this. We know that. We know this fact. We know that nil radical of A is intersection of all prime ideals. That is, nil A is contained in P for all P belong to spec A. That implies nil A is contained in M for all M belongs to max spec A. Any proper ideal is contained in a maximal ideal. We are using that fact. Then what is nil A is contained in the intersection. It is in the for every ideal, every maximal ideal, so it is in the intersection. Max spec. So nil A is in Jacobson radical of A. This holds for any ring, but we need to prove the reverse inclusion also for the polynomial ring. Okay, so what is the proof for reverse inclusion? That we take an element from Jacobson radical. Proof of the main problem. So what is the proof for the reverse inclusion? Jack X.
ওয়ান মাইনাস এক্স এফ এইটাকে কনসিডার করো, তারপরে ওই আগের ইয়ে থেকেই হবে, এই দুইয়ের ইয়ে থেকেই হবে। ওয়ান মাইনাস এক্স এফটা কনসিডার করো, তো ওয়ানটা
What is F? What is F? What is F?
A0 A1
What is
A2
F?
এগুলো তো
What is F?
ইম্পর্টেন্ট।
What is F?
ও এফ এফটা নীল রেডিকাল অফ এক্স থেকে একটা এলিমেন্ট দিতে হবে। এফটা nilpotent if and only A0 A1 A2 all are nilpotent। এবার কি করতে হবে, 1 প্লাস x টা কনসিডার করতে হবে। এবার তারপর 1টা তো নিডার A0 A1 A2 সব কত।
Which inclusion you are proving?
হ্যালো,
Which inclusion you are proving? You are taking an element from?
রিভার্স ইনক্লুশন।
Yes. So
নীল রেডিকাল অফ এক্স।
yes. Go ahead. So what do you want to? So what do you want
যদি
to prove?
একটা যদি নীল রেডিকালের মধ্যে থাকে তাহলে
Okay, if F is in nil radical, okay. So you are what is F? You are taking F from nil radical,
তাহলে
okay.
A0 A1 A2
Yes. They are nilpotent.
হ্যাঁ, এটা হচ্ছে কি সামেশন AI x টু দি পাওয়ার i।
Okay.
তাহলে এটা f এর চেহারাটা কেমন হবে, সামেশন AI x টু দি পাওয়ার i, তাই
Okay.
তো?
Okay.
হ্যাঁ, এবার এখানে A0 A1 A2 সবকটা nilpotent।
Okay. Okay. So Okay, so we prove. Okay, so we have this inclusion. Nil radical is contained in Jacobson radical. We need to prove the other inclusion. That is, we will take an element of Jacobson radical and show that it is inside the nil radical. So how will you show that? So suppose f is in Jacobson radical, we need to show that f is in nil radical. That is, each coefficients of f is nilpotent. And how will we show that? We take an element from Jacobson radical, say f equal to a0 plus 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 a n xn. We need to show that all of the coefficients are nilpotent. How we will show that? Any idea how to show that? The proof is a bit tricky. Any idea? Please discuss. I mean, this is supposed to be a discussion session. Please discuss. Rahul Oyon, any idea how to show that?
No.
Okay, so what property of Jacobson radical do you know? Jacobson radical is, I mean, very special because there is some nice property about Jacobson radical. Okay, so
That 1 minus if it belongs to Jacobson radical, okay, the
Yes.
1 minus if G
yes,
or G belongs to
yes,
H.
this one,
Right.
this and if and only if condition.
Yeah, if and only.
Okay, so we will using that. So we take an element f from, okay, so let's go back here. We take an element from here and we want to show that it is here. So let's f equal to a0 plus 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 a n xn is in Jacobson radical. Then I want to use this proposition. How can I use it? I want to use this proposition. How can I use it? You are actually correct. Now, how can we employ that proposition to prove our goal?
Then take some f from Jacobson of H,
Yes.
like a naught plus a1x plus dot 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 a n x equal n.
Yes.
Then 1 minus x f, that is 1 minus a naught x minus dot dot dot
Yes.
a n x to the power n plus 1 will be unique.
Yes.
And then
Yes, you are correct. Yes, you are correct. Then
previous result, we will get a naught to a n are nilpotent, I think.
yes, you are done. Pinky, do you have any other solution? Yes. Suppose f equal to a0 plus 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 an xn belongs to ax such that f belongs to Jacobson radical of ax. This implies 1 minus x fx is unit in ax. This implies 1 minus a0x plus 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 a n xn plus 1 is unit in ax. By exercise 2, 1 we have a0 dot 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 an unidempotent. This implies f is nilpotent. F belongs to nil ax by exercise 2.2. Yes. So this is a tricky proof. Not that much, but yes, the trick is some trick is involved here. Okay, so problem number 5. Yes, that's a nice problem. Okay, so anyone how to show that? How to, yes, till 1 am. At least I need to take a 2-hour class.
Mandatory.
Yes. So okay, so give so any idea how to solve this problem number 1, 5.1? Any idea? Please speak up. Please interact.
No.
Okay, that's the most expected answer. So first of all, tell me, suppose I give you the series of sign. I give you, for some x belongs to real number, I give you the I give that sin x equal to some series expansion, Taylor series expansion of sin x. You have a Taylor series expansion of sin x. You want to find the Taylor series expansion of cosec x. How do you do that? For some x such that sin x is not equal to 0. For sin x not equal to 0, you want to find the Taylor series expansion of cosec x. How do you do that? We do it occasionally in analysis. We have a series, we invert the series, and we want to find the multiplicative inverse of that series. And how can we do that? We have done lot of
By differentiating?
no. Not by differentiating. For sin x you have some relation between sine, cosine, and all that, which is a trigonometric function.
Yeah.
But for any arbitrary thing, you don't have any relation. I am giving you the example to give you some hint that how we can prove that. We did these problems in analysis in complex number theory, and suppose I have sin z, I want to find cosec z. So how I am finding that? I have sin z, cos z, I want to find the series expansion of tan z. So how I can find that, the particular series expansion? Okay, which side do you think is trivial? One side is trivial, right? The other side is problematic. Which side do you think it is trivial?
We say
The straight one, the straight one. If is a unit, then
If f is a unit, then if a0 is unit, right? This side is trivial. And what about the other part? Suppose f is unit. F is a unit. This implies fg equal to 1 for some g belongs to a power series ring x. Let g be mxm, m equal to 0 to infinity. So if g equal to 1 gives a0 b0 equal to 1, this implies a0 is 1, a0 is unit. I am just comparing the coefficients from the both side. Comparing the coefficient. Okay. So what about the other part? Suppose a0 is unit and you want to construct and g such that f is such that fg equal to 1. How can you construct such an f, such a g? Sorry. How can you construct such a g?
we can construct inductively, I guess. But the
Yes.
terms inductively. Suppose there exists some g.
Suppose what is suppose
Sure,
there is
sorry,
you need to
g
construct.
not the term g. Okay.
You need to construct some g.
First, let us assume the existence of such g exists such that f
Then,
dot g equal to 1.
if-
Let us assume.
Okay, then-
For the rough.
Then
Okay. Then write the general term of f dot g.
okay. Then
Are you writing something or what?
no. I am just indicating you. Then
Okay. Then let us compute the general product of the general term of g term by term. First, let us compute the constant term of g, which is obviously the inverse of a naught. Okay. Then let us compute g1 and let us assume that b1. Let us assume that we know the from b0 to bn minus 1 term, and we will compute bn by induction. I guess that
yes,
will help.
that's the idea actually. So we do some back calculation. Suppose such a j exists. That is fg equal to 1. This implies a0 b0 equal to 1, a0 b1 plus b0 a1 equal to 0, a0 b2 plus a1 b1 plus a2 b0 equal to 0, and so on. Now what you have? Now you have a0 b0 equal to 1. This implies b0 equal to a0 inverse. Now from this equation, a0 b1 plus b0 a1 equal to 0. Now from this equation you want to find b1. So what is b1? It is minus b0 a1 multiplied by a0 inverse. That what is b0? This is minus a1 a0 in minus 2. Now from a0 b2 plus a1 b1 plus a2 b0 equal to 0. I know a0 and a1. a0 is a1. Okay, no, I know a0. I want to find b2. b2 is a0 inverse. Here comes minus a1 b1 plus a2 b0. I know what is b1. b1 is, okay, there is another minus. Okay, minus a1 square, there is an minus. Yes, a2 b0 is a0 inverse. So b2 is equal to a1 square a0 a1 minus 2 a0 minus 3 minus a2 minus 2 and so on. So from this technique you can find out each and every term of g, and now if you take g such that so g like that, then if you take product and this becomes 1. So you have f. Okay, now back to the main problem. You have f. You know a0, f is some a0 plus a1x plus dot dot dot. You know a0 is unit. You can put b0 to be a0 inverse, b1 to be this, b2 to be this, and then take the product. You have fg equal to 1. If we take b0 equal to a0 inverse, b1 equal to, what is b1? a1 a0 minus a1 a0 minus 2, b2 to be a1 minus 2 a0 minus 3 minus a2 a0 minus 2 and so on. We will have take 0 and set g x to be summation bm xn m equal to 0 to infinity. Then we have fg equal to 1. Done. What else needed? Problem 2. So f is nilpotent, then all the coefficients are nilpotent. The same technique. Reduce it to the modulo mod p. So you need to prove that again. I mean, if a is an integral domain, then power series is the integral domain, and then the same proof. Okay, I need to prove it again. Fact. Suppose a is an integral domain, then is an integral domain. Proof. Let f equal to n xn, n equal to 0 to infinity, g equal to summation bmxm m equal to 0 to infinity belongs to power series ring such that if g equal to 1, this implies no, if g equal to 0, so this implies summation a n x n bm xm that is 0. This means a0 b0 plus a1 b0 plus b0 a1 ax plus a0 b2 plus a1 b1 plus a2 b0 x square and so on equal to 0. Comparing the coefficient, from both sides, we have a0 b0 equal to 0, a0 b1 plus b0 a1 equal to 0, a0 b2 plus a1 b1 plus a2 b0 equal to 0 and so on. Since A is domain, either a0 equal to 0 or b0 equal to 0. If a0 equal to 0, that implies b0 a1 equal to 0, that implies b0 equal to 0 or a1 equal to 0. If b0 equal to 0, this implies a0 b1 equal to 0, this implies a0 equal to 0 or b1 equal to 0. So in any case, you have either b0 equal to 0 or b1 equal to 0. So this 0 means one of the...
We know a0 equal to 0 or b0 equal to 0, right?
Yes, at least one of
So
them.
let us do in general that a0 equal to 0. Okay, then we can write the first function as some multiple of x, right?
What?
I am telling that suppose a0 equal to 0,
Yes.
then we can say f equal to some x into f1x.
Oh, okay. Yes. Take the x command.
And x is not a non-zero zero divisor, right?
Yes.
Then again we came to that f1 into g equal to 0. Okay. Then again conclude that
Understand. Take the
yes,
x command.
that way it will be much easier.
Take the x command, whatever. I mean the
And
process.
continuously it will continue that a0, a1, a2 all would be 0. Because if it terminates at some point, we can show some contradiction again that.
Yes. So I mean, if in one of them is 0, suppose a0 is 0, so a0 is 0, we will end up, so either b0 is 0 or a1 is 0. If b0 not equal to 0, then a1 is 0. If a1 is 0, a0 0, a1 is 0, we put here, this goes out, we have, if b0 is not 0, a2 is 0 and so on. So we have that either f equal to 0 or g equal to 0. And the ions process also same.
I guess first we tell the lemma that x to the power n is not a non-zero zero divisor. Okay. After that, conclude that there exists some a naught and b naught such that or ai bi such that ai and bi not equal to 0. Choose the first term, which is non-zero. Then multiply it, you will get the constant term would give you 0, but none of them are 0. But we know that A is an integral domain, so we can conclude.
That will also
Is
work.
it clear to everyone?
That also works. Anyway, we need one proof. We have two proof now.
That will be much nicer,
Yeah.
I guess, and much clean.
Yes. Of course. So okay, whatever we want one proof. We have two proof, and one proof is very nice. So whatever we have proved that a power series ring is integral domain if A is an integral domain. So back to the proof. So okay, so suppose F belongs to nil AX. Okay, let F belongs to nil AX. Let P belongs to spec A, and consider the map theta AX to A mod P power series ring X. Suppose summation A0 no A n x n n equal to 0 to infinity maps to A n plus P x n n equal to 0 to infinity. Okay, so observe theta is surjective and kernel theta is yes, hence Ax mod Px is isomorphic to A mod Px. Okay, so if F belongs to, since F is nilpotent, this implies theta F is also nilpotent, right? That implies theta F is 0 as A mod P X is integral domain. It is 0 means summation A n plus P x n equal to 0 plus P n equal to 0 to infinity. Now this 0 means A n plus P equal to 0 plus 0 plus P for all n union 0. This implies A n is in P for all n belongs to n union 0. This implies A n belongs to intersection P belongs to spec A for all n belongs to n union 0, since P was arbitrary. Okay, so this implies A n belongs to nil A for all belongs to n union 0. This proves that first part, that is, what is the problem? Yes, so we have proved that if F is nilpotent, then all the coefficients of F are nilpotent. So what about the converse? Is the converse true? If all the coefficients are nilpotent, then then F is nilpotent, like the polynomial ring. We have seen that in a polynomial ring, if all the coefficients of polynomials are nilpotent, then F is nilpotent. Is the same holds here?
It's obviously not true. Otherwise, they will
Why?
told us to prove it.
Why?
Otherwise, they have told us to prove it.
I mean, What? I mean, what is the logic behind that? It is not true.
Otherwise, they would give it as an exercise and prove it.
Okay. So this is your logic. So this is your logic. Okay. Now what about this problem? Problem 8. Some of you may know that what is Noetherian ring and all that. So I think Oyon knows that. What do you mean by Noetherian ring?
Yes, after some time the sequence will terminate.
Okay, so what about the problem 8?
Can you kindly show it on the screen?
Oh, okay. So problem 8 is saying that if the polynomial ring is Noetherian, then is A is necessarily Noetherian. Okay, let me show that. Okay, so here is the problem. Is it visible? No, I guess not. Okay, yes, it is now visible, I think. So problem 8, if Ax is Noetherian, is A is necessarily Noetherian? What can you say about it? Ayon, please respond.
I'm thinking about it.
You know that if A, okay, think about it. So according to your logic, A should not be Noetherian, right? According to your logic, A should not be Noetherian.
I didn't give any logic.
You say that if it is not Noetherian, otherwise Atya will not left it as an exercise, or Atya did not ask the question that is the converse to and whatever. So nice.
Oh, you are taking it as serious logic. Oh, sorry,
Okay, no,
misunderstood.
not a serious logic, but whatever. So okay, if it is not true, then what is the counter example? If it is not true, what is the counter example for this?
For which one? Question number 5 or question number
5
8?
2 question. Oh, what are you? Okay, 5 2.
What are you talking about?
Question number 5 2. Question number 5 2. You said that the converse is not true. So what is the counter example? Or any idea how to construct a counter example?
First of all, the constant term would not be a unit.
No, the converse is true means if all the coefficients are nilpotent, if S nilpotent. A0, A1 dot A, for all I, AI is a nilpotent. So is whether F is nilpotent or not. So you said that F is not nilpotent. So what is the counter example? In this case,
Okay, simply take F as a sequence 2 plus 3x plus 2x square plus 3x cube and so on.
where?
I guess.
In the ring?
Z, yes.
In the ring?
Yes. Then Z6 Z6.
In the ring Z mod 6.
Yes.
Okay.
I hope it will work.
So in the ring Z mod 6, you are saying that 2 is nilpotent. 2
Oh
2
no,
square.
sorry. I was thinking about the zero devices, not need
No,
potency.
no,
Wait.
no. The funny thing is Z mod 6 is isomorphic to Z mod 2 plus Z mod 3. These Z mod 2, Z mod 3 are integral domains, so they don't have any nilpotent element, right? So in the product ring they also have no
Yes,
important element.
just click Z4. I guess Z4 it should work.
Okay,
Take
in the ring.
no. And Z4 also it won't work. So let me think.
Okay, so
I just need two different nilpotent element. Okay.
I am showing you some more stuff. Before giving the counter example, I mean you are giving constructing some counter example. I am showing you that this problem number 2. Atiya also indicated the problem. Let A be a Noetherian ring and F is in power series ring. Prove that F is nilpotent if and only if each n is nilpotent. Okay.
Okay, so then first of all we cannot take A as a Noetherian ring, right?
Yes. You cannot take F as a Noetherian ring or any finite ring. Yes. Now I also don't have the example right now, but the idea is like
I guess it will be some ring of functions or some.
the idea is like that. Suppose A0 has nilpotency. I mean by nilpotency I mean the smallest n for which A is 0. A power n is 0. Okay, let us discuss something. N equal to 0 for some n, then a n plus k equal to 0 for all k greater equal to 0, right? So if A is nilpotent, you have a minimal n for which n equal to 0. I am calling that n as a nilpotency of A. So suppose A0 has nilpotency n0. Okay. A1 has n1, like AI has ni. If n0 is strictly less than n1, is strictly less than n2, I mean the sequence is strictly increasing sequence. N0, n1 is strictly greater than n0, n2 is strictly greater than n1. If you can construct, if you can find such thing a0, a1, a2 ... and then nilpotency is kept increasing, strictly increasing, then you cannot product the whole thing. I mean you don't have any number such that if you take the power and it becomes 0, right? If your nilpotency kept increasing, then you cannot do that. The idea is the following. But for in general, I mean if A is Noetherian, then you don't have such thing, right? Then you cannot have such thing, and you have, and the chain must stabilize and all that, and therefore you can say that okay, F is nilpotent if all the coefficients are nilpotent. But in general, in the non-Noetherian case, you don't have any such thing. Then you can choose n0, n1 increasing, and then you can say that F is not nilpotent in spite of having all the coefficients are nilpotent. So that's the idea. I don't have any example right now, so I will give any example if I have after some time. Oyon, is it fine? I mean it is not fine, but is the
It's fine.
is the idea correct? Is the idea, I mean
Yes.
okay, so what about the problem 5.3? F is in Jacobson radical if and only if A0 is in Jacobson radical. how to show that? Pinky? Pinky, Rahul, Ayun? Any idea? Hello? Pinky? Pinky, have you done that? Problem 5-3? Anyone please respond. I mean, please give your idea at least. Problem 5-3.
5-3 এটা করিনি।
Why?
ওটা দেখার সময় হয়নি 5-3 এটা।
What about 5-2 converse part? Okay. Problem 3. Suppose A belongs to AX such that F belongs to Jacobson radical. So you need to show that constant coefficient is in Jacobson radical of A. Let F is look like an xn n equal to 0 to infinity. Since F is in Jacobson radical, 1 minus yf is unit for all y belongs to A. What does that imply? 1 minus y into A0 plus 1 minus no. Okay, no problem. 1 minus y a1 into x plus dot is unit. This implies 1 minus y a0 is unit in A by problem by 5i and for all y belongs to A, and this implies A0 belongs to Jacobson radical of A. That's the if and only if condition. If A is in Jacobson radical, if and only if 1 minus ya is the unit for all y. So that's all. Converse part. Suppose if not in Jacobson radical, that is there exists some g such that 1 minus fg is not unit. Let g be m x m equal to 0 to infinity. Now 1 minus fg is not unit. Now 1 minus fg is not unit implies 1 minus a0, what is b0, is not unit by again phi 1. This implies a0 not in Jacobson radical of A. Proved. Is the proof clear? Please look at that proof and say, and if you want to ask something, please say, is the proof clear? Hmm. 27, what is 28? Okay, no. Okay, the problem 5 4. The part is belongs to max peak A for any m belongs to max peak x. Okay, using that fact, okay, if you look at the problem, said Atiyah said that the contraction of a maximal ideal of power series ring is a maximal ideal of A, and and M is generated by M contraction and C. So using that, I am proving the second part. I cannot prove that first part, so I will postpone the proof and I will give it the later. So right now I am proving the second part. Okay, so we know that M contraction is in max peak. I am assuming that. Okay, know that M contraction is in M. Since X also is in M, we have M contraction comma X. The ideal generated by this is in M. If we can show that this ideal is maximal ideal, then we are done. We have M contraction and the ideal is in M, so the ideal generated by them is in M. We need to show that this ideal is a maximal ideal. So we proceed as follows. First of all, give a morphism, say pi, so A to A, and then call it theta, A to M contraction. What is the map? F goes to F0, and then take any A and send it to A plus M contraction. Okay, since pi theta are ring morphism, are ring surjective ring morphism, surjective. Theta compose pi, is also surjective ring morphism. We want to compute the kernel of this map theta compose pi. Let F belongs to kernel theta compose pi. This is, that means theta compose pi of F equal to 0 plus m contraction, that is theta of F, this is F0, 0 plus m contraction, this is, that is F0 is in m contraction. Okay, F0 is in m contraction, and this is an if and only condition actually. If it is in m contraction, then that holds. So so kernel theta compose pi is all such that f of a is in m contraction. Now I am claiming that this set is same as this. This is my claim. Okay, so x is in here, fine. Take any element from m contraction, this is also here. Note that m contraction comma x is in kernel theta compose phi, and the reverse inclusion is obvious. I mean, if you take any yes, it is inside f. If you take any f, if the constant term is in m contraction, and the rest of the term is here, so it is here as x is in kernel theta compose pi, and any a belongs to a contraction is an element of kernel theta compose pi. The reverse inclusion is trivial. Take any element, it is of this form. So f0 is in okay. Suppose f is of the form a0 plus a1 x dot 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 dot. So we know that a0 is in m contraction, and this part, this whole part, take the x common, a1 plus dot dot. A0 is in m contraction, this part is in m, this part is somewhere else, I don't care. X is in that ideal, so this product is in ideal, so this is in the m contraction comma x. So we are done. It's trivial. Implies kernel theta compose pi is that m contraction comma x. Now m contraction belongs to max spec. A implies a mod m construction is filled, and by first isomorphism theorem this quotiented by m contraction x is isomorphic to a mod m contraction. This implies m contraction comma x is in max spec a power series ring. This implies m contraction comma x is same as m, because we have this, because m contraction comma x, the ideal generated by m contraction x is already inside m. M is the maximal ideal, this is the maximal ideal, therefore this has to be the same, because any two maximal ideals are either same or they have any proper intersection, they cannot be contained in each other. That's the definition of maximal ideal, the maximal element in the collection of all ideals. So since both of them are maximal ideals and one is contained in other, both of them are same. So this proves the second part of the problem. And the problem 5 says that, where is that? Problem 5 says that every prime ideal of A is contraction of a prime ideal of X. So you take a prime ideal from there and contract, it becomes a prime ideal. That's fine, but you have to show that every prime ideal of A is of the form of some contraction of some prime ideal. Okay, let P belongs to spec A, B and prime B are prime ideal. Okay, consider the ring morphism A AX to A mod PX theta. Note that kernel theta equal to this, and AX mod this is isomorphic to A mod PX. This implies PX is in spec AX. So we have found a prime ideal relating to a prime ideal of A. So claim P equal to PA intersection A. One side is obvious, P is in. Okay, proof of the claim. Okay, do not use the different. X, now take an X from P, okay, no, from the reverse one. Take an X from contracted ideal. This means okay, this is same as Px intersection A. This implies X is in P. This means all such element that is in Px. So obviously, oh no, observe P contraction is same. This means all such F belongs to AX such that F is in A. So this contains P, at least P is in this PXX contraction, reverse inclusion. So PXX contraction is all such okay, no, not all such F belongs to Px such that F is in A. So P is in this set. Take an element, so it is in A. That we have no problem. The reverse inclusion. Take an element here and show that is in P. So P, okay, so let X belongs to there. y belongs to there. This means this implies y here, y is in here, and y is in here. This implies, now write y to be summation a n x n equal to 0 to infinity. This implies a n belongs to P for all n belongs to n union n is in P by definition for all n belongs to n union 0. This implies all such, okay, so what is P contraction? All such that is in A. So this implies that y is in P. Because y belongs to A implies a n equal to 0 for all greater equal to 1, and this implies a0 is in P and y equal to a0. This means Px contraction is contained in P. Therefore P equal to, so we have found for given any prime ideal P of A, we have found a prime ideal such that its contraction is P. Okay, any doubt, please? You can ask if you have any doubt. I guess we can stop it here.
না বুঝেছি রে।
Okay, you may leave now. The class is over. The class is over and you may leave now.